So, rockets working in space. Never bought it myself. I propose that you need something to push against in order for a propulsion. And since there's no atmosphere, it's a vacuum in space, there is nothing to push against. So I was going to start by showing this video of Apollo 11 launching to go to the moon back in 1969. This is the one with Neil Armstrong and Buzz Aldrin. And you'll notice in this video that the rocket starts out ascending vertically, but as time goes on it starts levelling out and flattening. And the reason they say that this happens is so that they can take advantage of the Earth's gravitational force, which gives them a slingshot effect to propel them into space, giving them a higher velocity to do so. Now, we are told that the reason we don't experience the force of us spinning at 1,000 miles an hour at the equator is because we have this atmosphere that's kind of in sync with the rotational spin of the Earth. Therefore we don't feel anything. And since gravity is a constant, I don't buy the idea that they're using the gravitational force of the Earth to slingshot themselves anywhere. You can see now the rocket's levelling off, and you will not find a single video anywhere of any rocket ascending vertically, much less actually going into space, leaving our atmosphere. None. You'll find none anywhere. You'll see that the altitude that's been superimposed onto the screen there at 25 kilometers roughly now, 26, 27, is increasing so quickly, even though the rocket is coming up to being completely horizontal. So it's horizontal now, and it's increasing in altitude: 40 kilometers, 41 kilometers, 42 kilometers, 43 kilometers. How can that be happening? So let's look at the textbook explanation of how rockets work, more specifically how they work in space. So I've got nothing against this guy. He obviously reads textbooks and absorbs the information within them, but like a lot of these people, they can't actually test these things for themselves. They rely on what they read and just accept it. So this guy his name is Robert J. Dolby. He's a member of the Royal Astronomical Society, and he's also the curator of the Wernher von Braun Rocket Academy. So let's listen to what he has to say on the subject.
In this brief video, we're going to answer the question, what makes a rocket fly? Now that question refers to all rockets and all missiles. They are all the same in this regard, and the short answer is Newton's third law, which states, for every action there is an equal and opposite reaction. Maybe you're thinking that's not helping your understanding very much at this stage and you want a little bit more detail. Okay, thinking caps on, pens and paper at the ready. I'm going to be asking questions later. Or do you feel that algebra and quadratic equations really aren't going to help you that much either? Okay, you're in good company. You'll find that there hasn't been a missile man or woman in the history of rocketry that has really understood why a rocket flies by looking at those kind of calculations and understanding the rocket equation. We actually get our understanding of how the rocket flies from a very simple understanding. It's related to that Newton's third law, and it's the reaction principle. Now the good news is the reaction principle is actually something that's easy to understand, because it turns out you're already very familiar with it. You might not be able to identify it and know what it is, but you're already very familiar with this idea of the reaction principle. Now, some of the times that you've thought about what makes a rocket fly, you may have got, if you're not already sure about how it works, you may have got a little bit confused by what you've seen. You may have seen, everyone has seen lots and lots of images of rockets taking off, and it's easy to think that there's a secondary action going on with the rocket pressing on the ground, and after it starts flying you might start thinking that the rocket is somehow pushing on the air, and that's how it's moving. So it's not always absolutely 100% clear as human beings when we see something that we can actually see cause and effect. All we can ever really see is one type of event followed by another type of event, and we tend to actually then add the causal action based on what we've actually seen and other things that we're familiar with. So in any explanation, I'm going to go from things that you're already familiar with to something that maybe you're slightly less familiar with. So the reaction principle, it's something you've encountered in very simple terms. I think everyone's familiar with this example of the reaction principle. Here's an example everyone's seen, the lawn sprinkler. It's the reaction principle obeying Newton's third that makes it rotate. And you must have felt the shower head moving in your hand as you turn the tap on and off like this. Again, it's the rocket's reaction principle in action. The rocket motor, the jet from the rocket motor, isn't pushing on something. It's not pushing on the ground. It's not pushing on the air. It is the very expulsion of the jet from the rocket nozzle of the rocket motor that causes an instantaneous and simultaneous motion of the rocket in the opposite direction. Remember, this is Newton's third law in play, which is that every action has an equal and opposite reaction. So the action in this particular example is the jet stream from the rocket nozzle, and the reaction is the movement of the rocket motor, and thereby the rocket body as well, in the opposite direction. And the beauty of that is, and the true power of the rocket, is that it can do this in the atmosphere of the Earth, it can do it underwater, believe it or not, and it can also do it in the vacuum of space. And it's specifically because it doesn't need to push on anything to be able to make its transit. And that's what makes the rocket fly.
Okay, let's have a look at the scientific method. This is one that I found on Wikipedia. It's as good as any, I guess. So at the top there, make observations. Well, I see rockets flying in Earth's atmosphere. I don't see rockets flying in space. Think of interesting questions. Do rockets work in space? Formulate hypotheses. What are general causes of the phenomenon I am wondering about? Well, perhaps rockets don't actually work in space, and that's why I don't experience the phenomenon of seeing them. Develop testable predictions. If my hypothesis is correct, then I expect A, B or C. Well, this is where we mere layfolk are most vulnerable, as it's virtually impossible for us to test. We have to rely on the big budget space agencies like NASA. The best we can do is observe from test what happens here on Earth, and to hypothesize about what would happen in space. So my hypothesis is that Newton's third law of motion needs a caveat. This being that only when a fulcrum is present, this being a mass for the action to act upon, will Newton's third law apply. If such a mass is not present, despite the presence of an action, then a reactionary force will not be observed. So gather test data. Relevant data can come from the literature, new observations or formal experiments. Thorough testing requires replication to verify results. So I'm going to show you my experiment in a few minutes. But before I do that, I just want to wrap up this scientific method, and we have to develop general theories. And the theories must be consistent with all other relevant data. So if you go to NASA's website and go to the rocket principles section, it says a rocket in its simplest form is a chamber enclosing a gas under pressure. A small opening at one end of the chamber allows the gas to escape, and in doing so provides a thrust that propels the rocket in the opposite direction. A good example of this is a balloon. Air inside a balloon is compressed by the balloon's rubber walls. The air pushes back so that the inward and outward pressing forces are balanced. When the nozzle is released, air escapes through it and the balloon is propelled in the opposite direction. Also from NASA's website, there's a downloadable PDF which is a simple experiment that you can do. It's aimed at children, to be fair, but as you can see here on this diagram, you get a straw and you pass a piece of string through the straw, I don't know, 5-6 meters long, tie the string off at both ends, attach a balloon to the underside of the straw with some tape, and blow the balloon up and let it go. Obviously we know what the results of that will be, but this is going to be the basis of my experiments. NASA seem to advocate balloons on multiple pages as a good analogue for a rocket, so I thought I'd go with it. So Newton's third law in action. So now to the interesting part, because I'm going to demonstrate in this next test that a mass most certainly is required to make a rocket move, or a balloon move in this case. So I'm just going to put up on the screen again the quote that the guy made earlier that I asked you to remember. It doesn't need to be able to push on anything to make it transit, is what he says. So I've taken a piece of paper and I've wrapped it around the rear end of the balloon and taped it top and bottom. So the nozzle is sort of in the curve of the paper there. So when I let go, the air will still escape from the balloon at the same speed. The balloon will deflate as quick as it did without the paper. So according to his quote earlier, this should still move, this should still transit at the same speed, because it's not reliant upon it pushing on anything. It's the mere fact that air is released from the nozzle that provides the reactionary force to propel the balloon. So let's have a look at what happens. So Newton's third law experiment, test 2. Well, that didn't move very far. Let's try another one. So Newton's third law experiment number 3. Newton's third law experiment number 4. Not looking good. Okay, Newton's third law, 5th and final test. Come on, we've got to see some movement. Just to show that there's no restriction whatsoever. So going back to NASA's rocket principle page, if you scroll down, it says that one of the most commonly asked questions about rockets is how can they work in space when there's no air for them to push against? And this is my exact question. The answer to this question comes from the third law. Earlier on in the page it describes a skateboarder pushing away a skateboard with his foot, and describes the effect and the fact that the skateboard will move much further than what the pusher moves, and explains Newton's third law this way. So it says, imagine the skateboard again. On the ground, the only part air plays in the motions of the rider and the skateboard is to slow them down. Moving through the air causes friction, or as scientists call it, drag. The surrounding air impedes the action-reaction. So the only factor that they're saying that air has on the rocket is drag on the actual body of the rocket and friction, which causes it to slow down and not be as efficient. So they're saying as a result rockets actually work better in space than they do in air, because obviously there's no air to cause friction. As the exhaust gas leaves the rocket engine, it must push away the surrounding air. This uses up some of the energy of the rocket. In space, the exhaust gases can escape freely. So what it's saying is that in space, the expanding gas from the nozzle of the rocket doesn't have anything to push away on. It doesn't have to push away any air, thereby it's more efficient and actually works better. However, the whole premise that it doesn't need air in the first place is my whole problem with this law. As stated earlier, I believe it needs a fulcrum, or a point of leverage, for the rocket to work. So in the balloon experiment that I've just done, the reactionary force is in the opposite direction of the nozzle of the balloon. So the nozzle is at one end, at the rear, and the movement that we experienced in my first test was in the complete opposite direction. So that part of Newton's third law works. There is an equal and opposite reaction. However, it still needs that leverage in order for it to work. I would give the analogy of trying to do a pull-up. If you pull yourself up on a bar, you can lift your own body weight. The bar, in this case, is the point of leverage, the fulcrum. If you try to lift yourself up just by merely standing on the ground, and just grab yourself by the waist and try and lift yourself up, you can't do it. This is because there is no leverage point. You're pushing against yourself. This, in my mind, is a perfect analogy of what we just experienced with my balloon experiment. The balloon needed a fulcrum, something to push against, in order to make it move. Now, you may have noticed that in a couple of the tests, the balloon actually rotated around the string, sort of radially, and this only further gives credence to my caveated addition to Newton's third law, because what was actually happening is the air escaping from the balloon was disrupted by the paper, and it was disrupted such that it was pushing air unequally from either side of the paper, because I haven't put the masking tape and the paper on exactly square, exactly perpendicular and centrally to the balloon nozzle. It created an imbalance, and it was pushing the air out of one side and caused it to rotate around the string, not in the direction that Newton's third law states that it should, which is the opposite direction to which the air is escaping. So let's wrap up the scientific method and see if there's any other theories out there that are consistent with our data that we've collected. So let's have a look at the rocket engine nozzle. And Wikipedia defines a rocket engine nozzle as a propelling nozzle used in a rocket engine to expand and accelerate the combustion gases produced by burning propellants so that the exhaust gases exit the nozzle at hypersonic velocities. Let's scroll down to atmospheric use. The optimal size of a rocket engine nozzle to be used within the atmosphere is achieved when the exit pressure equals ambient atmospheric pressure, which decreases with altitude. So atmospheric pressure is air pressure. So right there in that first sentence, they are saying that rocket nozzle design and efficiency of such is dependent upon the ambient atmospheric pressure, the air pressure, which decreases with altitude. So for rockets travelling from the Earth to orbit, a simple nozzle design is only optimal at one altitude, losing efficiency and wasting fuel at other altitudes. So what they're saying there is, in an ideal world, they would have a nozzle that changes its shape and its dynamics as altitude increases, because there's only, if it's a fixed shape, there's only one altitude at which it's at its optimal. So let's go down to the vacuum use. Now, the whole premise of this video is that I don't think rockets can work in a vacuum. So the first sentence that it says here, I think, is applicable if you remove the word vacuum, because it describes high altitude. So let's read it. For nozzles that are used in very high altitude, it is impossible to match ambient pressure. Rather, larger area ratio nozzles are usually more efficient. So right there they're saying that at high altitude the ambient air pressure is so negligible that they need to put much larger ratio nozzles on to account for the loss in air pressure. So again, air pressure is small at high altitude, therefore larger area ratio nozzles are more efficient. If you take this to its logical conclusion and traverse into space where air pressure is zero or very near to zero, how big or what area ratio nozzle are you going to need then? Would this be infinite? Do you see what I'm saying? So if we go back to look at what NASA claim on their Rocket Principles webpage, they claim on the ground the only, and I must stress that word that they use, the only part air plays in the motions of the rider and the skateboard, or in our case the rocket, is to slow them down. Moving through the air causes friction, or as scientists call it, drag. So they are claiming that the only part air plays with rockets on the ground in the Earth's atmosphere is the drag effect that's caused by friction on the body of the rocket itself. Nothing to do with the propellant dynamics. So they are claiming the exact opposite of what Wikipedia are telling us, because they're telling us that there's only one altitude at which a particular shape nozzle or size nozzle is optimal, and that they have to actually increase the nozzle ratio as altitude increases.
Button Moon, we follow Mr. Spoon.
We're getting closer to Button Moon. Who's going to press the round button to land? It's not going to be Egbert, because he can't reach the button. So Tina's going to press the round button for him.